Ames, could you get the door? We've dealt with transformations before. We've dealt with transformations before. You are comfortable with 90% of transformations. But the last transformation we are going to get into today makes everything complicated. Okay? Makes everything complicated. So I'm going to give you a different technique to be able to handle transformations by just focusing on a table of values or focusing on points. So I have this function 1 over x squared plus 1, and I'm going to focus on some points, -2, -1, 0, 1, and 2. If I plug in -2, I get a fifth. If I plug in -1, I get a half. Plug in 0, I get 1, and it's symmetrical. Get that? Okay? We know from the past that if you subtract 1 on the outside, what happens to the graph? Tell your neighbors. What happens if you have subtraction f of x minus 1? Yeah, everybody answers correctly, like it's going to go down 1. Correct. But I'm going to say, oh, that takes my y values and subtracts 1 from them. I can recreate my table, and we're not worried about formulas. I can recreate my table that I have up here. You see this table up here? I can recreate my table where my x's don't change and my y's, we subtract 1. Okay? -5/5 plus a fifth is -4/5. A half minus 1 is -1/2. 1 minus 1 is 0. A half minus 1 is -1/2. -4/5. We can create the points easily by transforming the points from the original function easily. We can see this. If we look at the table, here's f of x, here's g of x, which equals f of x minus 1. You can see my y-coordinates are the only ones that changed. I have, for my original function, this is my original function off of f of x, -2.2, -1.5, 0, 1, 1.5, 2.2. I subtracted 1. -4/5, -1/2, 0, -1/2, -4/5. Adjust your points, and it might be easier to do the transformation. What happens if you have an x minus 1 inside the function? Tell your neighbors. Yeah, you guys are all correct on that stuff. You're saying we're going to go right 1. Well, how do you adjust points right 1? Tell your neighbors. Add 1 to the x. I can take my x values from my table and add 1. So I can just change my table, starting from my original function. The y's aren't going to change. I'm going to keep the y's where they are. I'm going to add 1 to all the x's, and all my x's go to -1, 0, 1, 2, 3, and then my points stay 1/5, a half, 1, a half, a fifth. All of a sudden, we are just able to do the transformation just by transforming my points, taking my x's, adding 1. You can see if I do f of x minus 1, I would change my x's to be -1, 0, 1, 2, 3, and my y's do not change. 0.2, 0.5, 1.5, 0.2, 0.2, 0.5, 1.5, 0.2. My x's that change, boom, I've shifted to the right one. Cool? Great. We understand outsides up and down, insides left and right. We understand when you're outside your function that it acts normal to what you expect it to do. Order of operations make sense to us, but when we are inside our function, it is opposite of what we expect it to be. We usually say x plus 1, oh, add 1 to your x's, but no, x plus 1 means subtract 1 from your x's to do that transformation. X minus 1 means add 1 to your x's to do that transformation. Does that make sense? Okay. if I show you that transformation, 1/2 times f of x, what would be the transformation? Describe it. Tell your neighbors. You don't have to shout out to me. Tell your neighbors. Now, tell me, what would you do to your point? So, this is a vertical dilation as expected. It's a vertical dilation by a factor of 1/2. It is as expected. To do this transformation, you could take your y values and do what you think to do. Take your y values, your function values, and multiply them by 1/2. That would work. I'm not going to do it, but you could. I think I'll do it. Whatever. We had the points -2, 1, 0, 1, 2. Let's create the graph again. -2, 1, 0, 1, 2. We had a fifth, a half, 1, a half, a fifth. Take your y coordinates, multiply by 1/2. This stays the same. This becomes a 10th, a 4th, a 1/2, a 4th, a 10th. It's very easy to do if you're just going off of points. You know, like verbally, what the transformation is. Well, you can convert it into what would you do to the points. You can see this if I have a 1/2 of f of x, that my point point 2 became 0.1, 0.5 became 0.25, 1 became, look, it's like perfect, right? What we're expecting. And now we have this 1/2 on the inside. We have not dealt with this yet. You might have talked about it last year in Algebra 2. The reason why we don't talk about it yet in this class is because it's very complicated and it's tough to kind of visually see until we get to functions that we're going to discuss in the second half, trig functions. So we have to introduce this now. What would you expect if you have this 1/2 times x? We haven't talked about it, but like talk about it with your neighbors. What do you expect? Now, it is tough for me to explain why, so I'm just going to tell you. Inside the function is opposite of expectation. You would expect, and it's easier to go off of like, what would we do, okay? On the previous one, we multiplied our y's by 1/2. You would expect to take your x's and multiply them by 1/2. That's wrong. Inside ends up working out reverse. It ends up being the opposite of the order of operations we think. It's kind of like going backwards. It's like we're solving an equation. It's kind of like using inverses. Turns out, if you have 1/2 x, you want to do the transformation, you would take your x values and multiply them by 2. Now imagine taking your x values and multiplying by 2. Okay, well, let's have our x and our f of x. We have the 1/5, 1/2, 1, 1/2, 1/5. Those aren't going to change. What changes is that -2 becomes -4. -1 becomes -2. 0 stays 0. 1 becomes 2. And 2 becomes 4. Now, what does that look like if I take my x's and multiply by 2? What does that visual transformation look like? Tell your neighbors. We have horizontally stretched it. Now, we don't like to talk about stretches and compressions in this class. They keep everything to dilation. A horizontal stretch is a horizontal dilation. A horizontal dilation by a factor of 2, because you're taking your x's and you're multiplying it by 2. Let's just see that in play. If I have the 1/2 here, we see this green graph has stretched things. Woods, lock it up. Stretch things horizontally. You might think that it's a vertical stretch, but look, this point here, 0, 1, does not move up. It does not go up at all. You might think, oh, are the points going up? No, they're not. Not all of them. This point is not going up. What is happening is that these points are getting stretched out. And I can show you 0.2, 0.5, 1.5, 0.2 by plugging in -4, -2, 0, 2, and 4. There you go. This point, -4.2, corresponds to that point, -2.2. It's just you have to plug in -4, then multiply it by 1/2 to get to this original point at -2.2. So it's that this point is pulled or stretched out from the y-axis. This point is stretched out. This point is not stretched at all. Notice it's not vertically stretched. This point stretched out. This point stretched out. Okay? So, multiplying by a number on the outside. Vertical dilation by a factor of A. You will take your y values and you'll multiply them by A. But inside, being opposite of your expectations, order of operations kind of going in the opposite way. It's like, what do you plug in to get to your original function? It's like backwards of what's going on. It affects things horizontally, we know that. But it will be dilating things, but by a factor of the opposite of what we expect. If I have 5 times x, my dilation is 1/5. If I have 1/5 times x, my dilation is times 5. You would take your x values, you would not multiply them by A like you would expect. You would take your x values and you'd multiply by the reciprocal. You'd do the opposite because of being inside and PEMDAS and reverse order of operations. You guys cool with that? Okay. What happens here? Tell your neighbors. It's really just a dilation. It's a dilation. You would take your y's and multiply it by -1. Well, what happens when you multiply all your y's by -1? We flip. We reflect. We flip. We don't have this. This is a vertical reflection. Now, you would not change your x's. You would just flip your y. Keeping to the table will help you. Okay? This was extremely hard to see using this function. So I'm going to change the function. Let's talk about f of x equals the cubed root of x. Okay, new table. X, f of x. The cubed root of -8 is -2. The cubed root of -1 is 1. The cubed root of -1 is -1. Cubed root of 0 is 0. The cubed root of 1 is 1. The cubed root of 8 is 2. What if there was a negative inside the function? What do you think would happen? What would you do? Would you do it to your x's? Would you do it to your y's? What would you do to your x's or your y's? Ready? This one's tricky because there's no like opposite of multiplying by -1. So you can divide by -1, but like that doesn't really change anything. That'd be the opposite sign, and yeah, you might think about that being the option, but in reality, this transformation, f of -x, would take your x's and you multiply them by -1. That means we have the point 8, -2, 1, -1, 0, 0, -1, 1, and -8, 2. What happens is that my graph of f of x reflects over the x-axis, reflects over the y-axis. If I change this to the cube root of x, there's the cube root of x. If I change this to f of -x, we can see this point here gets vertically reflected, or really horizontally reflected. It doesn't reflect down here. It's this point comes there. That point ends up over there. Okay? Cool. It was a vertical reflection. So, it was a horizontal reflection. Negative f of x is a vertical reflection. F of -x, horizontal reflection. The vertical reflection reflects over the x-axis. Horizontal reflection reflects over the y-axis. Now, come down here to the bottom. Say what? Oh, we were paying attention, right, Cold Ticket? I was not writing that fast. The answer is like, I would be able to figure out how many days it would take to get to a certain level.
I just said, oh yeah, I wrote that. I said days based on. No, that was. You just flipped the word.
Yeah. Just flip it. You'd get a level after a certain amount of days. It's like, oh, how high would it be 10 days later? Here, it's like, how many days for it to get to a certain level? Okay. Go to the bottom. What gets really tricky, but we'll try to keep it as simple as possible. But again, you got to remember, inside, opposite of expectation.
Yeah.
Inside is opposite of expectation. It's reverse order of operations. We talked about it when we talked about why we move right versus left when we add or subtract. I have some function f of x. G is equivalent to taking f and doing the following thing. Dilating the graph of f vertically by a factor of 7. Go. Where does that 7 go? Write it down. Everybody's doing this. You can do it. I believe in you. Oh, Georgia fan. I didn't even know. Vertically dilating by a factor of 7. I've set something up for you. Where does 7 go? Here's 7. Where does it go? There. Where's it go?
It's 7 f of x. Or f of x. Oh, no, we said opposite. So.
Whoa. Vertical, outside, normal. Okay? So, vertical, outside, expected. Horizontal, inside, opposite. So, a 7 on the outside, correct. Okay. Next. Horizontal dilation by a factor of 11. Where does it go? On the inside, 1/11. It is opposite of my expectations. Now, here's the thing. If you write this down, let's say you were given this and you're like asked, what would you do? This is telling you multiply your x's by 11. Multiply your x's by 11 so that, like, let's say we wanted to get to f of 2. We'd have to plug in 22. 22 times 11 is going to get me to 2. Okay, great. Now, translating down 4, everybody, translating down 4, where does that go? Go, write it. Minus 4 on the backside, correct? And then, finally, write 12. No. Write 12. Now, this is where we're all gonna be wrong. No. Here we go. Let's go back. Let's go back to this guy. All right. Let's say we dilate this by a half, not by a factor of 2. We dilate this by a factor of 2. Pay attention. Horizontally dilate this by a factor of 2. I'm glad you're focused and you're locked in here, Linda. Okay. Here is my dilation. Let's say I want to shift this over 2. Let's look at the easiest point to look at, 0, 1. Let's say I want to shift this to the right 2. This point, 0, 1, should end up at the point 0, 2. Would you agree with me? Great. How do I shift things to the right 2? Linder, tell me. Minus 2. Here it comes a minus 2. I should have the point 0, 2. What the heck? I just jumped past it and got to 0, 4, 1.
You have to factor it out.
Oh. Hold the phone. It's the fact that this 1/2 x is the dilation. Let's take this x right there and let's subtract 2 in there. What ends up happening is that 1/2, that PEMDAS, that reverse order of operations comes into play. We think we can just subtract 2 and we're going to shift it right. It's like we horizontally dilate and then we shift right. But it's the fact that inside is funky. Inside is funky. Inside is opposite of our expectation. Even though, listen, even though you would think shift right 2 first, then horizontally dilate by 2 second, you're wrong. It's like, I don't know, maybe Cole Trickett should be teaching. I don't know why I'm even bothering. We will need to understand that even though this looks like we're shifting right 12 first, then horizontally dilating, it's not. It's the opposite order of operations as we expected. And this is what's the trickiest about horizontal dilation and shifts. Okay. No. This. Can we lock in? What are the transformations that you see in here? And what is the order in which that happens? I'm going to give you an x value. Here's an x value of 9. Let's say I have an x value of 9. Okay? I'm just going to give you that. There's an x value of 9 somewhere.
It's 15. It goes to 15.
Okay. Okay. Let's say I have a point on a function, and the point is 9, 1. Here's the point on the graph of f of x, 9, 1. Now, I want to transport that point. I want to transform that 1.91. Okay. What does the minus 6 do? What does the 5 do? Tell your neighbors, what does that minus 6 on the inside and the 5 do on the inside?
That is right side 6 and 1 is horizontal back.
Okay. There are two options here. You could either go right 6 and then dilate by 1/5. That would take your x value, add 6, and then multiply it by 1/5. Am I right? Please, everybody take your x value, add 6, multiply by 1/5. What do you get? Good. So we get 3. So we think that we are going to get this x value 3. That will go to a y value of 1. All right, let's double check. Let's plug in 3 into G. What's 3 minus 6? What's negative 3 times 5? Wait, hold on. If I plug in 9, I better get 1. You just told me that if I plug in 3, I should get 1. You were wrong. It is not right 6, then dilated by a factor of 1/5. This is what you expect. Because you see this and you look at order of operations and you say, oh, the minus 6 is happening first, and then the 5 happens next, but inside is opposite. So you were all wrong. Instead, let's do this for me. Please dilate this, or take your x's and multiply it by 1/5 first, and then add 6 to move it right 6. Take this 9, divide it by 5, add 6. What do you get? Now, you have to do some math, but do it. 39/5. Great. Brunton says, I think this point should get transformed to 39/5 1. Well, let's see. If I take 39/5 and plug it in, I'm going to subtract 35. I get 9/5. 9/5 times 5 is 9. Oh, f of 9 is 1. That's right. So once you throw in multiple dilations, it's even more, or multiple horizontal things, it's even more important to think against what you want to do. You all want to go right 6 first, then divide by 5 or multiply by 1/5. Don't. Go to your homework.
Wait, are we like that?
No, we're doing some homework examples so you don't screw up when you get to your homework.
I'm sorry.
Okay, team. Let's look at the graph on the right. Let's look at the graph on the right. Please look at the graph on the right. What I'm telling you is that to do transformation, sometimes what's best, I'm breaking up this pro table next class. Sometimes what's best is to just transform your point. Okay? So, I listed off some points. Find some space on your homework, whether it's like to the right or in the middle or up above, to list off the points of this function I guess that's j. Well, no, this is g. This function is g, and then we're going to transform into j. Okay, so list off these points. I got you don't have to copy down. Look at the points and write them down. 1 point at a time. Okay. You see, our first example is this. What I think is the easiest, might not be for you, but what I think is the easiest to do is to take those numbers, negative 1/3, 1/2, and 1, and to translate it into the transformation, and then go a step further and say, oh, this is affecting my x's this way. Oh, this is affecting my y's this way. And say, these are the operations I will do on these points. I will do this to the x's, I'll do this to the y's, and boom, I have new points on my transformation. So, please, start with negative 1/3. What do you think that would do?
Divide by 3.
No, tell your neighbors, Woodsy, you're shouting out, but I know you're really not paying attention until it's like time to answer something. Like, how about you guys, as a bro table, work together and say, what's the transformation and what would that affect?
This would affect the vertical. And it would not only flip it, but
What about the 1? What about the 1/2? Okay. Now, outside is normal, as expected. I would take my y's, multiply them first, and then add. So, my yellow transformations are take my y's, multiply them by negative 1/3, and then add 1. Please do that with your y's. Oh, let me show you how to do that. Take 6 times negative 1/3 becomes positive 2. Add 1 becomes positive 3. My first j coordinate is going to be 3. What will be the x coordinate that corresponds to that point? Well, let's go to our other transformation. That's this 1/2. What does the 1/2 do? It horizontally dilates. Opposite of how we expect it. We would take our x values and multiply them by 2. This would be a horizontal dilation of a factor of 2. So I would take the corresponding x value and multiply it by 2. You can do that with all 5 of your points, and boom, sketch your transformation quickly and easily. Go do that.
Are you stopping?
Yes, because you're not doing what you're supposed to do, and you're just waiting until it's like, oh, when Mr. Messner calls on something, I'll answer, and that looks like I'm a good student.
Me?
Who?
Yes.
Go ahead. I would like the graph as well. Go ahead and sketch the graph.
I think I did it wrong.
I got 3. I got 1. I got 2. I got negative 1. I got 0. I got negative 4, 0, 4, 8. If you plot those points and connect them, you have successfully vertically dilated, vertically shifted, and horizontally stretched / dilated by a factor of 2. I don't think it looks like that, but that's you just not graphing points correctly, I think.
Like this, right?
Let's see. -4, 1, 0, 2, 4, -1, 8, 0. It looks like it goes joink, 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 joink. It should have some curvature going on there.
There we go.
If you tried to do this by eyeballing it, it would be tough, trust me. But now, that one's not the tricky one. The next one on the bottom right is. We have J of X, which is now G of 1/2 of X plus 2. Now, focus, because this is the important thing. This is what's weird. Let's just start with this -4, 6 points. I'm going to move it down. No, I can't move it down. -4, -6 points. You guys all know that this is shifting to the left too, right? Okay, so you know that there's going to be some -2 in there. You guys all know that this is a vertical dilation by a factor of 2. You guys know that you'll take your x's and multiply it by 2. The question is, do you multiply 2 then subtract 2, or do you subtract 2 then multiply by 2? That's the question. You all get the same thing, that's for sure. Thank you, Linda, for paying attention. It is not PEMDAS. You would think you would subtract 2. And here's how you're going to check, guys. You would think subtract 2, multiply by 2, you get -6 times 2, you get -12. Okay? You would think you'd have the point -12, -6. But if you plugged in -12 and then added 2, you get -10. Multiplied by 1/2, you get -5. No! I have -4. So -12 is not the same transform point as -4, 6 transform. So this is not right, even though we think it is. Inside, opposite of expectation. We take this x value, multiply it by 2, is -8. -2, you get -10. If I plug in -10, add 2, it's -8. -8 times 1/2 is -4. Oh, that would give me G of -4, which is -6. If I plug in -10 into this x, do the manipulations, boom, you'd get -4, which gives you -6. Yes.
Can you multiply a half with x and then x over 1?
Yeah. But it doesn't really help you. So, okay, cool. So, you guys do the rest. Inside, opposite of expectation. You would think subtract 2 first, then multiply by 2. Hell, your first expectations would be add 2 to your x's, then multiply by 1/2. But again, we're kind of undoing things. We're reversing, we're like inversing things. If we find the inverse, you multiply by 2, but then subtract 2. Honestly, this is a brilliant discovery.
Mine doesn't.
No.
Mine doesn't look like
No.
that.
Because your y's are changing. Why are your y's changing? Your y's shouldn't change at all. There's no change in your y's. It's just your x's. Times 2 minus 2 is -4, -6. -6, 0. Times 2 minus 2. 0 times 2 minus 2 is -2. -2, -3. Times 2 minus 2. 2. 2, 6. Times 2 minus 2. 8. 7, 6. 3.
What do you, look, my wife is saying, but I was talking about something
Whoa, yeah.
I don't think it's like, what is that?
All right, are we done?
Yeah, this is right. I'm telling you, right.
Now, let's look a little bit. As long as you have those points plotted correctly, you're fine.
Oh, yeah.
Okay? Great. Now, some other questions you're going to see. Hey, we have the function f with a domain and a range. Here's the transformations of your function f. You got f of 3x plus 2. What is the domain and the range of your transform function?
Do it all out. You do to multiply. You can do a third, and you add 2 to the range, right? Yeah.
Your y's will be added by 2. That's your range that you would add 2 to. Your x's are being dilated by a factor of 1/3, opposite of what you're expecting. You would take your x's, which is your domain, and you'd multiply them by 1/3. Right? Nancy? You're just waiting to get out of here, huh? Get out of here. You got stuck today. Yeah, true. This table sucked today. How about that?
We got everything right.